So now that we know about collision theory, let's talk about the 5 factors that affect a rate of reaction and how do these factors affect collision theory in a way to either speed up those collisions happening or slow them down. So our 5 main factors are nature of reactant, concentration, temperature, surface area, and catalyst. So these 5 factors are often adjusted in order to maximize successful collisions. So let's talk about concentration. Increasing the concentration of a reactant will increase the number of particles that we have per volume of solution or in a gas phase. So what will happen here is the more particles that you have, you're going to have more collisions. Here's a couple of good graphics right here. So they're showing you, these few molecules moving around and colliding, but you don't have as many when there's not as many particles. The minute you increase the concentration and you add in extra particles, you're going to have more collisions. And this is a good thing because this is going to increase the frequency of collisions. And make a note of this. This is going to affect whether you have proper alignment or proper orientation for your collisions. Increasing concentration has no effect on activation energy, but it does have an effect on trying to get the proper alignment. When we increase the temperature of a system, what we're doing is we're increasing the kinetic energy of those particles. And so we know that if the molecules are moving faster, the odds are good that they're going to collide more often with each other. If they collide more often, the chances of us having proper orientation or proper alignment goes up. And it also allows our molecules now to collide with more energy. So we satisfy the activation energy requirement as well. So out of all of the factors, temperature is our favorite. Okay, so we like to maximize temperature. That's supposed to be a smiley face because that satisfies alignment and it also satisfies activation energy when you have your molecules moving around that much faster with higher kinetic energy. Changing the surface area of a solid reactant, okay, this only applies to solids, this does not apply to liquids or gases, will increase the rate of reaction. And the reason that this happens is because if we increase the surface area, we now have more particles available to react. So this is a good image right here where we see a solid lump of something. And we see that only the outside atoms here, or outside molecules, can interact with your other reactant molecules. So you're really limited as to how many collisions you can have. The minute you increase surface area right here, and you break apart all those particles, they can all now interact with the other reactant particles, and then they increase the frequency of those collisions. And again, hoping to have proper orientation or proper alignment. Surface area does not affect activation energy. A catalyst is also a factor that can affect the rate of a reaction. So when we have a catalyst, the catalyst acts to speed up our reaction. An inhibitor will slow it down. But typically in chemistry, we like to talk about catalysts. Catalysts speed them up. The catalyst is also not consumed. So when you add a catalyst to a chemical reaction, I mean, obviously it's there originally because you're adding it into your reaction, but once the reaction is completed and you form new substances, that catalyst is actually still there in its entirety. Okay, it does not get altered, it does not get changed, it does not get consumed, it does not go towards making products. It just is there, and the only job of the catalyst is to change the activation energy barrier. So a catalyst will lower the EA barrier on, if you think of it graphically, and if an activation energy of, 200 kilojoules was required, a catalyst might only make the requirement 150 kilojoules or 100 kilojoules. And because a catalyst only affects the activation energy, it never affects the enthalpy of a reaction. So when we look at the effect of a catalyst graphically on a potential energy diagram, what we notice here, this is again exothermic reaction. We can tell because reactants have a higher potential energy than our products. And so here is two types of reactions, one that is uncatalyzed in blue and one that is catalyzed in red. And so the uncatalyzed reaction has quite a decent EA barrier right here. But when you add a catalyst, the catalyst lowers the activation energy barrier. You see it right here. There still is one, but it's less. And so this is why now your molecules don't need as much energy. The reaction can happen faster and catalysts speed up the reaction. But notice that the potential energy of your reactants, potential energy of your products do not change. And remember, this is how you calculate enthalpy in a potential energy diagram, and catalysts do not affect the enthalpy of your reaction. The last factor that we'll talk about is nature of reactant. And this is probably like the least used factor, simply because a lot of times the reaction that you are trying to carry out is very specific and you don't want to switch out reactants. So sometimes the nature of reactant doesn't really apply in a lot of scenarios, but sometimes it does. What it does mean is that when we are changing the nature of a reactant, we are either swapping in or swapping out a reactant that has more or less potential energy. Okay, so reactants have, a lot of potential energy. And if they do, oftentimes the reaction happens faster. If a reactant doesn't have a lot of initial potential energy, then we need one of those above 4 factors in order to speed up the reaction. So change the temperature or surface area. But changing out the nature of a reactant can only be done in a few ways. So for example, if it was feasible to do so, gases have higher potential energy than liquids or solids. Solids have very, very low potential energy. So there's an example of maybe maintaining the identity of a reactant, but changing the state into the gas phase, which would have more potential energy. If you were doing a reaction with an acid, for example, maybe you could swap out a strong acid versus a weak acid if it worked. And then another example is our activity series of metals that we learned about in grade 11. And we just know that some metals are more reactive than others. Perhaps if you are carrying out a certain reaction and you can swap out metals, that would be an opportunity to do so.